traditional ADHM-like descriptions are not known. Okay? Traditional ADHM description, like the traditional description of the SU3, which failed in 2 dimensions. Okay? We even don't know that. But once we know our alternative gauge theory, we can easily construct a 2-dimensional anomaly-free gauge theories, which we claim to be corresponding to the instanton strings to the G2 and SO7 with exotic matters. So this, from the instanton counting perspective, is another surprising application that we find. So let me basically try to explain to you how we get the alternative ADHM-like description for the, let's say, for the SO7 with some matters. Because once you get it, you can fix it to obtain the G2 as well. So the basic idea here again is to construct the UV gauge theories for the instanton strings or instanton particles. And the UV gauge theory can be sacrificing some of the inference symmetry that you require, like supersymmetry. But here, not just supersymmetry. Let us consider SO7 gauge theories instantons. And the SO7 is the case in which we know the standard ADHM instanton quantum mechanics or quantum field theory. But we don't use that because we are not interested in that this time. But we only focus on the SU4 or SO6 subgroup of SO7, and we seek for UV gauge theory for instanton on the instanton world volume, which manifestly realizes this subgroup only. So we're sacrificing some of the flavor symmetries compared to the traditional ADHM quantum theory. So the standard SU4 ADHM gauge theory is given this way, and like before, like to render anomaly cancellation, you can put in lots of extra n equal 2 multiplets given in this way, and you can introduce the following matter contents forming multiplets having to do with the 2 matters in spinning representations. They are anomaly free, and then give rise to the correct partition functions. And once you have this, you can Higgs this 6-dimensional system down to G2 and SU3, and you can introduce the corresponding deformation of that to obtain the ADHM-like description for G2 instantons. Further Higgsing gives the alternative SU3 theory that I explained. And you can do the instanton calculus for the quantum mechanics to start with, because even for ADHM, even for, let's say, for G2 5-dimensional gauge theory, the systematic ADHM-like approach for G2 instanton particles have been unknown. So you do the partition function calculus for G2 instanton quantum mechanics, you again get some contour integral and the rest sum. And in all cases that we could check, it agrees with the existing formula for the G2 instanton partition function, computed from various indirect methods. We can go steps forward to explore the regime in which no computation has been done for G2 instantons by adding, let's say, some matters in fundamental representation, and these are new predictions of our networks. And by doing the gauge theory-like construction for G2 and SO7 with exotic matters, we can construct a self-theory string quantum field theory in 2 dimensions for this exotic atomic construction. And starting from that, we can consider much more complicated and richer self-theory strings. Okay. So I can conclude with a few remarks. I try to explain to you with a very specific example that we could get solid quantitative results concerning self-theory strings and 6-dimensional quantum field theories. But the progress is happening in various other examples and in various different ways. Especially in today's talk, I explained to you the progress related to the exceptional instantons ADHM-like descriptions. And I explained to you how to compute the Nekrasov instanton partition function, or self-theory string partition function, the tensor branch. And it could be more interesting to know how we could use this tensor branch observable to study the conformal field theory's symmetric phase. There were many proposals suggested for that, and we could explore the 1-0 conformal field theories this way. Generalizing what we have found for other exceptional instantons would also be exciting. We're trying hard, but I think we should have more ideas to have instanton counting problem for all other exceptional instantons satisfactorily done. Another comment that I'd like to give is that our 2-dimensional quantum field theories living on the self-theory strings are related to another very challenging 4-dimensional conformal field theories called 4-dimensional Argyres-Douglas theories. So we have already heard about Argyres-Douglas theories in a talk this morning, and the Prine Agarwal, right in the next session, will also talk about something on Argyres-Douglas theories. But the point I would like to to raise is that it's well known that if you compactify these Argyres-Douglas theories in a suitable way on the two-sphere, when you take the two-sphere side to be 0, you'll get a two-dimensional conformal field theory exactly living on the self-theory strings that I have explained to you today. Okay? But Argyres-Douglas theory may be regarded as a much more difficult quantum field theory than the two-dimensional theory I explained to you. But there are progresses happening on Argyres-Douglas theories in many ways. We heard about some progress this morning. Many other people are getting quantitative progress. But one progress I'd like to mention is by my colleague Prarit Agarwal together with Mariyoshi and Jaewon Song. And they tried to find, and they found certainly four-dimensional Lagrangian description for quantum field, for Lagrangian description for Argyres-Douglas theories, in the sense that if you flow the algae flow of the Lagrangian that they found, the infrared fixed points are asserted to be the strongly interacting Argyres-Douglas theories. Okay? So the Prarit will talk about that in that session. But the point is that if we compactify this there Lagrangian on two-sphere, apparently you're getting a completely differently looking quantum field theory in two dimensions than I presented to you. But we should be able to check whether there are non-trivial dualities between these quantum field theories, let's say by studying elliptic genus and so on. So it will be a very interesting direction. So the final interesting direction that I'd like to mention, which I think is one of the most interesting subjects in this field, should be that the elliptic genus is a partition function of self-theory strings or a torus. So it highlights the S-duality transformation properties of the six-dimensional partition function on R4 times T2. For instance, if you focus on the simplest maximally superconformal theory in 6 dimensions, this torus compactification is giving rise to 4-dimensional maximal superangles, which is known to enjoy SL2Z property. And this S-duality or SL2Z properties are nothing but the SL2Z acting on the torus. Okay? So for the 6-dimensional 2-0 theory, its R4 times T2 elliptic genera are nothing but the 6-dimensional uplift of the maximal superangles instant of partition function. And if you view this Nekrasov partition function from the self-theory strings elliptic genus point of view, this S-duality transformation property becomes much more transparent, using which one can really study the so-called high temperature limit of this Nekrasov partition function to study 6-dimensional physics. And the reasoning is as follows. So if you compactify the 6-dimensional theory of the torus, you can regard one direction as a spatial compactification direction, another direction as a temporal, Euclidean temporal circle direction, whose radius is something like inverse temperature. So we compactify this system to get 5-dimensional quantum field theory, specifically Yang-Wu theory, but we're eventually interested in the 6-dimensional physics, in which the circle size becomes larger. So in the compactifying limit, lots of mysterious 6-dimensional physics are expected to show up. Okay? So, but S-duality, if you remember the geometric meaning of it, is S-duality is nothing but changing the two sides of the torus in the case when the torus is rectangular. So if you know the low temperature limit or the small radius limit of the partition function, you can use it to infer what the large radius or decompactifying limit of the partition function is. So using that, we were able to, it's an ongoing progress with one of my students, we could deduce what the high temperature limit of the Nekrasov partition function is, and surprisingly using this S-duality, we could find that this high temperature free energy is scaling like n cubed, which is the first occasion, I think, which n cubed scalings of degrees of freedom are microscopically found in thermal free energy. Okay? And lots of interesting related physics can be done in the context of 6-dimensional 1-0 theories as well. There are much more interesting physics having to do with phase transitions, relation to 4-dimensional and 5-dimensional isolated CFTs and so on. So I think using this elliptic genus picture, there could be lots of interesting things. I finish here. Thank you.
Any question or comments?
So because they didn't see that you came on the model and so can you see some background dependence?
Yeah, the Carroll parameters. If you have some the Calabi-Yau, its various Carroll parameters physically mean, among many others, let's say the size of the various two cycles, and physically that corresponds to the scalar expectation value in the tensor multiplet in 6-dimensional CFT. And if you change these parameters in, and the corresponding meaning of these scalar parameters in the context of index is the number of the self-zero strings. That's because, you know, if you have some finite volume 2 cycle in F theory, you can wrap D3 grains on it many times to obtain the string-like configuration, which is the self-zero strings. So the Coulomb web of this cycle corresponds to the string winding number, roughly speaking, the chemical potential for that. So the Kähler parameter dependence, strictly speaking, it's not the Kähler parameter dependence, it's the chemical potential dependence of the string winding number. But that chemical potential is in one-to-one correspondence with the Kähler parameters of Calabi-Yau.
2D perspective, can we say?
In the 2D perspective, can we see these
Okay.
Kähler parameters?
Yeah, you can.
Okay, so yeah, in the 2D perspective, what happens is the following. As I explained to you, the Kähler parameter of Calabi-Yau in the effective field theory, you know, it's the expectation value of this. Okay, so this sets Yang-Mills coupling constant in 6-dimensional gauge theory. So that's the Kähler parameter. And if you do the instanton counting, if you have k instanton numbers, it is weighted by this instanton action, right? So it's naturally interpreted as the fugacity corresponding to the string number. Okay? So this is the fugacity factor for the k strings. And if you do the instanton string calculus, this is the semi-classical action that k instanton shows. So this Yang-Mills constant is naturally, Yang-Mills constant, coupling constant, or Kähler parameter is naturally mapped to the fugacity for the string winding.
So your 2D theory seems external much hypermarginal. Does it have additional moduli parameter of the?
Oh, because I added lots of other matters?
Yeah.
You know, the thing is that, you know, if this ADHM theory is quantum mechanically consistent, it gives rise to right moduli space, but it suffers from anomalies. So I added lots of additional matters, but I want the infrared moduli space to be unchanged. So I introduced lots of matters, but I introduced potentials to make them all massive. So in the infrared, the light fields form the same moduli space, but the heavy fields suddenly become light only at the singularity. So it provides a UV completion. Yeah, that's the structure.
And you can also introduce some omega background.
Yeah, I already introduced omega background everywhere in my talk.
I see.
Yeah, yeah.
So that's the hyperkähler structure.
Oh, you mean how the gauge theory changes in omega background? Oh, yeah. So omega background can be introduced only after you compactify the theory on torus. So R4 is the transfer space, and torus is where the self-zero string is wrapping. So you can view this omega deformation as a kind of twisting between this R4's rotation and this torus circles. So rather than taking as a direct product, you take as some twisted product, and then you can introduce omega background, and which can be incorporated in the gauge theory action as well.
Any other question? If not, let's thank the speaker again.